All right, here's another example we didn't get a chance to talk about in lecture today. So in this example, we have a merry-go-round as a common piece of playground equipment. A 3-meter diameter merry-go-round with mass of 250 kilograms is spinning at 20 rotations per minute. Note that RPM is a shorthand for rotations per minute. John runs tangent to the merry-go-round at 5 meters per second in the same direction that it's turning and jumps onto the outer edge, and John's mass is 30 kilograms. So let's draw the situation so far. So here's a merry-go-round. I drew two versions of it because we're going to look at before and after. So before John jumps on, basically the merry-go-round is spinning with some omega initial. And if the merry-go-round is spinning in this direction, basically John runs towards it so that when he jumps on, he's also moving in the same direction as the merry-go-round. So we'll go ahead and draw John here. And John is running towards the edge of the merry-go-round with a velocity of 5 meters per second. And then afterwards, now John has jumped onto the edge, and the whole thing is spinning together with some omega final. So first thing we ask ourselves, can we make a claim for angular momentum being conserved? So if we include in our system both John and the merry-go-round, then there are no external torques being applied to our system. So if we were looking at just the merry-go-round, well, then by jumping onto here, John does apply a torque to the merry-go-round, but we're going to include John in our system. So our system is John plus the merry-go-round, and we're going to look at the total angular momentum before John jumps on, and then we're going to look at the total angular momentum after John jumps on. So our main equation here is L total initial is equal to L total final. Well, our initial situation is made up of a spinning disk and a linearly moving point mass. So we treat John basically like a point mass moving this way at 5 meters per second. So for John, we're going to use R cross P, which is basically RMV, when R and P are perpendicular to each other. So R is coming out here. So let's talk about that in pieces. Right before John is about to jump on, basically when John gets here, John is moving this way at 5 meters per second. So right before John lands on the merry-go-round, is running this way, John's momentum vector P is going to the right. And the R vector basically goes from the axis of rotation, which is at the center, to here. So when we do a cross product of two perpendicular vectors, we essentially get magnitude of R times magnitude of P times sine of 90 degrees. And sine of 90 degrees, as we've mentioned many times, is just 1. So the sine part just gives you a factor of 1. So L total before is L of the disk initial plus the angular momentum of John initial, which is equal to L total finally, which is basically the angular momentum of disk plus John final. And let's just use the shorthand D for disk just to be uniform. There we go. All right, now we need to find each of these pieces. Well, L of the disk is moment of inertia of the disk times omega initial. And L of John, as we just talked about, so for L John initial, we're essentially doing R crossed into P, which is magnitude of R times magnitude of P, which is MV, times sine of 90 degrees. So angular momentum of John is basically RMV. And this is mass of John, by the way, equals, now we need to find the total moment of, so afterwards it's going to be I of disk plus John times omega final. Now to find the I of disk plus John, let's do each of them. We need to find I of the disk, we need to find I of disk plus John. So let's work on I disk first. If I have a disk that's rotating about its center, I can look up in my table the moment of inertia of a disk is 1/2 mr squared. So 1/2 mass of the disk times r squared. If I plug in the mass of the disk, which is 250 kilogram, and then the radius, which is going to be 1.5 meters, because this is the diameter of the merry-go-round, that means that the radius of the merry-go-round is 1.5 meters. If we plug that in, you'll get that the moment of inertia of the disk is 281.25 kilograms meters squared. Then we need to also find the I of the disk plus John. Well, moment of inertia of the disk plus John, and just to be consistent, I apologize, this D should be capital because we're just using capital D for all the disk. That's going to be 1/2 m mass of the disk times r squared. Oh, whoops, sorry. Yeah, that's going to be the moment of inertia of the disk that we just calculated plus moment of inertia of John. Well, John is a point particle that is some r away, so John's moment of inertia is just mr squared. So for any point mass, we just use mr squared for I. So this is I disk plus mass of John times r squared. You already found I disk about the center is this, so you can plug that number in, plug in John's mass, plug in 1.5 meters for John's radius, and we get that this total moment of inertia should turn out to be 348.75 kilograms meters squared. So now we're basically ready to plug everything in here, and what we're solving for is omega final. So I'm going to symbolically do this first. So omega final is I of the disk times omega initial plus how far John is jumping on, which is the radius of the disk, mass of John times the velocity of John. All divided by basically this term to get omega final by itself. So divided by I of disk plus John. For I of the disk, we're going to plug in 281.25. For omega initial, it's given to us in rotations per minute. I've shown the workup here to figure out what it is in radians per second, so that's 2 pi over 3. So for omega initial, I plug in 2 pi over 3. For this r, I'm plugging in basically the radius of the merry-go-round, which is 1.5 meters. Mass of John is given to us as 30 kilograms. Velocity of John is given to us as 5 meters per second. And finally, I of the disk plus John, we calculated here as 348.75. Once you plug all those numbers in, you get omega final is equal to 2.33 radians per second. I highly recommend that you plug in the numbers and justify it to yourself that you get the same number, because for the multiple choice questions, you have to be able to do these calculations reliably to get full credit. And the question asked us to give us what the merry-go-round's angular velocity is in RPM. So I now need to convert this to rotations per minute, and I'm not going to show the work for that, but basically, if you follow this work to go to radians per second from rotations per minute, you need to kind of invert that whole process to go back to rotations per minute. So I want you to check your answer. You should get 22 rotations per minute when you convert it. All right. So make sure you try each detail, try this problem on your own, and make sure you justify all the details, because I am just showing you the expressions and writing the numerical answers, so you should be able to calculate this on your own.